Section 10.1, Integer Exponents. So let's go ahead and look at an example that will lead us to a negative exponent and then see how to deal with that. So they're asking us to simplify y to the third over y to the seventh. So one way I could attempt to deal with that is to use the rule that says if you have a division where the bases are the same, then you subtract the bottom exponent from the top exponent. So that would be y to the 3 minus 7. And if I do that, I get y raised to the negative 4, and I think that leads to the natural question, what does that mean? Y to the third means that we have a multiplication where there are 3 y's, but how can you have a multiplication where there's negative 4 y's? It's a confusing idea. So let me look at y to the third over y to the seventh and simplify that a different way. I could say that on the top I have y to the third, and in the denominator I have y to the third times y to the fourth. Notice that would still be the 7 y's just from here. I'm just splitting it up. And then at that point I could say this y to the third cancels that y to the third. So then what's left over? Well, in the denominator there's a y to the fourth. In the numerator everything's canceled, but when that's the case there's still a 1. So notice both times I started with y to the third over y to the seventh. One time I got y to the negative 4. The other time I did the work a different way and I got 1 over y to the fourth. If both of those methods are valid, then what that would imply is that both of these answers must be the same. So what does y to the negative fourth mean? Apparently it means the same thing as 1 over y to the fourth. So that's going to be our rule. Let's look at that as a definition. For negative integer exponents, if n is a counting number and b is not 0, then b to the negative n is 1 over b to the n. So that's just making the statement right here. If we have something raised to a negative power, we can get rid of that negative by doing the reciprocal, 1 over that base, and now the power is positive. So in words, define b to the negative n, take its reciprocal, and then you change the sign of the exponent. So essentially, how do we deal with negative exponents? We get rid of them. How do we get rid of them? By taking a reciprocal, because that changes the sign of our exponent. And then there will be times where we actually start off with the negative exponent in the denominator, but if we follow these words, we could still get rid of the negative by taking the reciprocal. And when you take the reciprocal, that brings the negative exponent up from the denominator to the numerator. So same words, in words to find 1 over b to the negative n, find its reciprocal, and then change its sign. Notice that's the exact same words both times. So if it's in the top, because you could think of this as b to the negative 1 over 1, then to get rid of the negative sign you move it to the denominator. If it's already in the denominator, think of this as over 1, then you move it up to the numerator. So let's look at a few examples of that. So if we have x to the negative 2, we want to take the reciprocal, make that 1 over x squared, and that changes the sign and the negative exponent is gone. If we're starting out with that negative exponent in the denominator, we bring that up to the numerator. That changes the sign of the exponent. We get y to the positive 5, and the negative exponent is gone. So those are the two basic examples of how this works. If you just have a regular negative exponent in the numerator or all by itself, you move it to 1 over, push it into the denominator. If it's already in the denominator, you get rid of that negative by bringing it up to the numerator. Now we're going to move on to some other types of examples. So on this one, 5 times x to the negative 3 looks fairly similar maybe to the first one, but the 5 out front does make a bit of a difference. And the key thing to understand is that the 5 has its own exponent. The number 5 is the same as just 5 to the 1, and then that's times x to the negative 3. So when we go to simplify the negative exponent, we have to realize that that only involves the x piece, not the 5 piece. So what we do is kind of separate those off. Think of it as 5 to the first over 1 times x to the negative 3 over 1. Because this piece is fine, we would just leave it alone. But because this piece has a negative exponent, we would do the reciprocal. Doing the reciprocal changes that exponent from negative to positive. And then we would just take what's left over and multiply it. 5 to the first, which is just 5 times 1 is 5. And multiplying across the bottom, 1 times x to the third is x to the third. And there's our simplified answer, 5 over x to the third. It's pretty common that when people see this example, they just do 1 over, and then they have the 5 down here. And that's because they're thinking of this 5x all being to the exponent of negative 3. But the 5 has its own exponent, which is 1 and is positive, So in effect, the 5 just stays where it is. So this is kind of the long way of looking at it. If I were to do this problem for myself, I would start off with that 5x to the negative 3, and I would think, okay, this 5, well, first of all, I think of it as like a fraction, and say the 5 has a positive exponent, so it just stays in the numerator, but the x to the negative 3 has a negative exponent, so that one kind of gets pushed down to the denominator, which is the effect that doing the reciprocal had on that. So when you have more than one factor, factors that have positive exponents just stay where they are, and then if you have factors with negative exponents, they have to slide across the fraction bar to change that exponent from negative to positive. So this is kind of the quick way to do it, and this is kind of the logic more drawn out. So doing it like this is fine, but this kind of explains the reasoning behind leaving the 5 alone. All right, let's go to the next page, look at a few more examples. On these next few examples, the main point that we're making is that the exponent rules we learned in the previous section still apply even when you have negative exponents. So we learned that if you're multiplying two things together and the bases are the same, you can add exponents, so that applies even if the exponents are negative. So this would become 4 raised to the negative 2003 plus 2000, keeping the base the same and adding the exponents. And then if you add those two together, since one's negative and one's positive, you're really doing the difference, and the difference between 2003 and 2000 is 3. But the bigger of the two numbers, this one is negative, so it would be a negative 3. So at that point, we're just using the exponent rules. We're multiplying two things with the same base, so we add their exponents. But now we have a negative exponent, so we still need to simplify that. So that would be 1 over 4 to the third, and then multiplying out 4 times 4 is 16, times another 4 would be 64. So the answer would be 1 over 64. And I want to go ahead and check that on the calculator in a way, and then show you something interesting about the problem that we started off with. So I can check it in the calculator in a few ways. I can just do 4 raised to the third and see that it's 64, so that matches with the 4 to the third going to 64. I could also take 4 and raise it to the negative 3, though that will give me a decimal, but I could compare that to the original 1 divided by, or the end answer 1 divided by 64, and see that it's the same. So we can kind of check it in that manner. But I want to show you something interesting. If we just took the original problem and tried to enter it in the calculator, 4 raised to the negative 2003 times 4 raised to the 2000, we get an error message, and it says overflow. And it's saying overflow not because this answer is too big for the calculator to handle, but taking 4 and raising it to the 2000 is too big for the calculator to handle. So it's trying to work out this piece and then multiply it by that piece, and it can't do this piece. So if we didn't know that we could use exponent rules, we would actually be stuck. Our calculator can't handle that one, but we can, because we know the rule about multiplying the same bases means add the exponents. And then other properties that we learned carry over as well. So we learned in the previous section that if you have one exponent raised to another, then you should multiply exponents. So this becomes y to the negative 3 times 4, or y to the negative 12. I would probably just go straight from here to there, but this is just showing the rule. We're multiplying. And then this can't be our answer because it has a negative exponent, and in order for it to be considered simplified, we have to get rid of the negative exponent. So just like we got rid of the negative 3 here by doing a reciprocal, we would do a reciprocal here as well and make that a y to the positive 12 down in the denominator. So there's the simplified version of that one. And then here we did problems like this before, and what we said is when you're multiplying these things, multiply the numerical parts together. So 5 times negative 3 is negative 15. And then multiply the variable parts together. So that'd be x to the negative 8 times x to the fourth. And because those are the same base, you multiply them by adding the exponents. So that's x to the negative 8 plus 4, which is negative 15 times x to the negative 4. And then because our exponent is negative, that's not considered simplified. And so what we're going to do is, so this is a little tricky. Sometimes people see the negative on the 15 and they think, oh, I should move that down to the denominator to make it positive. But moving something from the top to the bottom changes the sign of the exponent, not the sign of the thing itself. So right now, negative 15 has an exponent. Let me do it in a different color. But it has an exponent of 1. That's positive already. If we moved it down into the bottom, we wouldn't get positive 15, we'd get negative 15 raised to the negative 1. That would be even messier. So that negative 15 is going to stay up top because it already has a positive exponent. And the x will move down in the bottom because it had a negative exponent. Moving it down to the bottom will make that exponent positive. So we get negative 15 over x to the fourth. All right, so there's a few examples of how we can just continue to use those exponent rules from previous section, even if the exponents are negative. So power to a power, multiply the powers and get the negative 12. X to the negative 8 times x to the negative 4, add the exponents, get x to the negative 4. So we're going to do those reciprocals to get rid of the negative exponents eventually, but when we first start off, we're just using the old powers from the previous section. All right, continuing on to page 3, let's go ahead and look at an example that involves negative exponents. A person plays an electric guitar outside, and the sound level, f of d, in decibels, at a distance d yards from the amplifier, is described by the equation f of d equals 5,760 times d to the negative 2. So simplify the right-hand side of the equation. So I'm going to just start off by copying the equation down. F of d equals 5,760 times d to the negative 2. Now when I wrote that just now, I put the dot for times, which isn't necessary, but one of the things it does kind of show us when we do that is that these are two separate factors. 5,760 is one factor, d to the negative 2 is the other. And what's important to realize about that is this exponent of negative 2 is just on the d. It's not on the 5,760. That number has its own exponent. I don't see one, but that means it has an exponent of positive 1. And what's important to realize there is that means when we get rid of that negative exponent, we're only going to move the d to the denominator and make that a d squared. We're not going to move the 5,760 down because its exponent was 1, which was positive, so that can just stay put. So that would be considered the simplified version of the function because it no longer has a negative exponent. And then they want us to find f of 8 and think about what that means in the situation. So first let's just find it. So f of 8 means that we're going to plug 8 in place of d. So we'd get 5,760 over, instead of d squared, it would be 8 squared. So that's 5,760 divided by 64 if I do the squaring on the 8. And then we just need to divide to finish that off. So 5,760 divided by 64, that goes in 90 times. And then to help us think about what this means, we want to think about the units. So first let me put units here. 90 what? Well, that's a value of f, and f is measured in decibels, so that would be 90 decibels. And then to think a little bit more about that, what that means, how did I get that? I plugged in an 8, but 8 what? Well, 8 went in for d, so 8 was a value of d, and d was the number of yards we were from the amplifier, so that represented 8 yards. So then I just want to put that into words and say, if we're a distance of 8 yards away from the amplifier, we hear the sound at a level of 90 decibels. So let's write that out. So at a distance of 8 yards from the amplifier, the sound level is 90 decibels. So I think that the key when you're trying to interpret one of these or say what it means in the situation is to think about the units. So when you get this value of 90, that was a value for f. So go up here and look, what are the units of f? Decibels. The number we put in, 8, was a replacement for d, so what were the units of d? Yards. And once I realize that it's 8 yards and 90 decibels, I can start putting it together into a sentence. Alright, continuing on, I want to go ahead and show you another application of negative exponents, and that is that it comes up in something called scientific notation. So let's look at that definition. A number is written in scientific notation if it has the form n times 10 to the k, where k is an integer, and either n is in between -10 and -1, or n is in between 1 and 10. So this number right here is in scientific notation because the number out front, which would be like the n, is 8.31, and that's in between 1 and 10. And this says the same thing, it just means it could be a negative number also, but basically we want the size of this to be somewhere between 1 and 10. And then it's written as times 10 to some power. So what happens when you multiply by 10? It just moves the decimal over once. So what happens if you multiply by 10 6 times? It's going to move the decimal to the right 6 places. So if I work this out and think, what does this number really mean? And that is our directions here. Write each of the numbers in standard decimal form. Then I take that 8.31 and I move its decimal to the right 6 places, because I multiply by 10 once, it moves. I multiply by 10 again, it moves. And I do that 3, 4, 5, 6 times. So the first couple times I multiply, it just moves it past the 3 and the 1. After that, what you need are placeholders of 0 that the decimal is moving after, or moving past. And so our decimal is no longer over here, now it's at the end, which means that we're now looking at the number, let's see, we've got 8, 3, 1, and 1, 2, 3, 4 zeros. Throw our commas in there to help us visualize that. Looks like that number is 8,310,000, and no ones or hundreds. Let's go ahead and look at another one. First of all, why would this be considered scientific notation? The times 10 to an integer fits the times 10 to the k piece, and the number out front, 6.488, is a number in between 1 and 10. So this would be considered scientific notation. And so to think about what does this mean, there's just a little bit like of a guess, I could say, where if multiplying by 10 to the positive 6 means move the exponent to or the decimal place to the right, probably if the exponent is negative, I would move the decimal to the left. And that does turn out to be the case, but I want to show you why using what we just learned about negative exponents. If you think of this as over 1, then this becomes 6.488, and then we could say we want to get rid of the negative exponent, and that would move that down to the denominator where it would become positive. So now when you have times 10 to the 6, you're multiplying by 10, and that's why you move the decimal to the right. The number's going to get bigger. But if you have times 10 to the negative 5, that's really the same as dividing by 10 5 times. And every time you divide by 10, it's going to move the decimal to the left. The first move would go past the 6. The next 4 decimal moves to give us our total of 5 would create zeros. So this would be 0.1, 2, 3, 4, and then in the 5th decimal place will be that 6, and then 4, 8, 8. It turns out this is not a coincidence. Whenever you have one of these that's negative, that lead number always ends up being in that decimal spot. So when I have a times 10 to the negative 5, that lead number of 6 ends up in the 1, 2, 3, 4, 5th decimal spot. So technically what's happening is the decimal's moving from here, 1, 2, 3, 4, 5 spots to the left, but that will always have the effect of putting that lead number in that decimal place. So what I try to remember here is that if you have a positive exponent, you're going to get a big number, and the exponent tells you how many places to move your decimal to get that big number. If you have a negative exponent, that means you're going to be dividing, and that means this is going to end up being a really small number, and the exponent tells you how many places to move the decimal to the left to create that small number. All right. So here's a summary of what we just saw in those last two examples. Let me go ahead and read it to you and then give you kind of my take on it as well. So if you're converting from scientific notation to standard decimal notation, the book says that to write the scientific notation for n times 10 to the k in standard notation, we're going to move the decimal point of the number n as follows. If k is positive, then we're multiplying n by 10 k times, and therefore we move the decimal point k places to the right. And if k is negative, then we divide n by 10 k times, and therefore we move the decimal point k places to the left. I think that rule is pretty good. I would just caution you against against memorizing this only. So I think if you said if k is positive, I'm going to move to the right, and if k is negative, my decimal is going to move to the left. I think that's really easy to get mixed up. So I think the middle part is very important. If k is positive, then you're multiplying by 10k times, and therefore it makes sense to move it to the right, because that's what creates a bigger number. If k is a negative exponent, you need to remember this part. That means that you're actually dividing n by 10k times, and therefore it makes sense to move the decimal to the left, because every time you divide by 10, a number gets smaller, and moving the decimal to the left makes that number smaller at the same time. Alright, let's go ahead and look at this from the other point of view real quick, which is, what if we have a number in standard notation and they ask us to put it into scientific notation? So let me pull in that previous page and that definition for you. So it says for a number to be in scientific notation, you have to have the lead part be in between 1 and 10. So if you want to take 280,000 and put it in scientific notation, you have to move the decimal from right here at the end to a place where the number would now be in between 1 and 10. And so if I put that decimal in between the 2 and the 8, then now we have a number that's 2.8, and 2.8 is in between 1 and 10. And then we would multiply that times 10 to some power, and the power would be equal to the number of places we moved the decimal, which was 1, 2, 3, 4, 5 spots. So it's either going to be a positive 5 or a negative 5, and what I would encourage you to remember is that numbers that are big have positive exponents in scientific notation, and numbers that are small, like this one, have a negative exponent. So we usually don't write all those zeros, so I'm just going to change this a little bit and say it's 2.8 times 10 to the 5th. Alright, and then let's look at another one. On this one, we want to do the same thing. Move the decimal so that after we're done moving it, this number is between 1 and 10, and 2.3 is in between 1 and 10. And then think about, alright, how many places did I move the decimal to make that happen? 1, 2, 3, 4, 5. So I'm going to go times 10 to some kind of power of 5. But if your number is going to be a small number, that's when you need the negative exponent. And if you're ever not sure if you put it in, right, take it out. Right? Take 2.8, multiply by 10 5 times. That gets you back to this big number. Take 2.3, divide it by 10 5 times because of the negative exponent. That'll take you back to this small number. So if you're ever unsure if you put the sign on there right, just work it back out the other direction and see if you get back to where you started. But the thing that I remember to make this quick for myself is big numbers have positive exponents in scientific notation, and small numbers have negative exponents in scientific notation. Alright, now that we've worked on the mechanics of scientific notation, let's go ahead and look at a few examples that use scientific notation. So the number of different 8-character passwords that can be made with 26 letters and 10 numerals as your choices is approximately 2.8 trillion. Write that in scientific notation, and then how did they get that value? So first let's start off with writing it in scientific notation. So we have 2.8 trillion. Let's try and write that just as a regular number. So one way to do that would be to say it's 2.8 times a trillion. So what is a trillion? That's 1,000. 3 more zeros, now we're at 1,000,000. 3 more and it's a billion, and 3 more and it's a trillion. So that's 2.8 times a trillion, which is just a translation of this. Now we could multiply those together, which would make this a 2 and that an 8. But if you're going to put it in scientific notation, let's go ahead and do that actually. So if we multiplied that together, the 2.8 times this really long number, we're going to get 2, 8, 0, 0, 0, 0, 0, that's those 3, 0, 0, 0, and then 0, 0, 0. So just to make sure that's trillions, right? We have millions, billions, trillions. So just a little over 2 trillion, so 2.8 trillion. So to put that in scientific notation, though, we would want to move back to this 2.8 version because we're supposed to move the decimal from the end of the number here in between, or after the first non-zero digit, so that this part's between 1 and 10. So 2.8 definitely fits the bill of being between 1 and 10. And then we'd multiply that by 10 to some power, and the power would correspond to how many places we move the decimal. So we can count those. So here it was, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spots the decimal got moved. So the exponent's either 12 or negative 12, and we start off with a big number, so that would be 2.8 times positive 12. in order to get all these zeros, you have to keep multiplying by 10, which moves the decimal over and gets to here. All right, so there it is in scientific notation. So why would we need scientific notation here? Well, first of all, why did they use the word trillion? Because they didn't want to write out such a long number, right? So one way to avoid writing out a really long number is to use things like this, altered units, trillions. Another way is to put it in scientific notation. And something interesting in terms of just the calculator, if I take 2.8, let me get rid of that old number, 2.8 times a trillion, so 1,000, million, billion, trillion, the calculator actually immediately says that's too big and puts it into scientific notation, 2.8 times 10 to the 12th, which is the same thing we had. All right, then in terms of where did they get that number, let's go ahead and look at that real quick too. So they're talking about an 8-character password. So we're trying to choose how would we fill in 8 slots if some online site told us to do a password and that we had the option of mixing together numbers and letters. So there's 26 letters, and then you have 10 different numerals from 0 to 9. So for each slot, that gives you 36 different possibilities. So you have 36 choices for what you would pick here, and then you have the same thing on every one of these. So every single option, you have 36 choices, and we'll learn a little bit more about this later on in the course, but when you have 36 options for 8 different things, the total number of options is 36 raised to the 8. So if you take 36, raise that to the 8th power, you get 2.821109997 E12. But notice the starting part, 2.8, and the E12 match up with there. So this is the work they did to come up with that answer, and then they just rounded it to the nearest tenth of a trillion to keep it as a simple answer. All right, let's look at some other examples. A beam of light can travel the length of a football field in about 30 nanoseconds. Express that in scientific notation. So of course the idea there is that light travels super fast, right? So we wouldn't maybe even notice it traveling, but it's going to be a very small amount of time that it takes for it to go from one end of the football field to another. They're telling us that that is 30 nanoseconds, but they want us to express it just in regular seconds because a lot of people, including probably you and I, don't know what nanoseconds means. So we're going to put it in regular seconds to maybe try and make it more common expression. But we need a little help. We need to know what a nanosecond is, and nano means billionth, so a nanosecond is a billionth of a second. Or another way of saying that would be, so we're going to do a conversion here. I'm going to try and get rid of the nanoseconds and replace them with just regular seconds. So if nano means a billionth, then it means it takes 1 billion of these nanoseconds to make just a single second. And so if we do that, we're converting, the nanoseconds cancel out, and then it would be a division, it looks like. So I could do this on the calculator and it would put it into scientific notation for me, but let me go ahead and show you the work by hand that we would do on that. So we have the 30, and then here, this is 10, let me do the scientific notation X type of marker. This is 10 raised to, the power would be the same as the number of zeros. Let me do that as 1 over, since it was a fraction. So there's 9 zeros, so that would be 1 over 10 to the 9th. But in scientific notation, you're not supposed to have a fraction like this. You're just supposed to have 10 to a power. So the next step would be to say, okay, well, 10 to the 9th in the bottom would be the same as 10 to the negative 9th in the top. That's a little unusual for us to go from a positive exponent to a negative, but in scientific notation, they want it to be 10 to some power, not 1 over. So if it was a positive exponent in the bottom, then if I push it back up to the numerator up here, it would become a negative exponent. This is almost scientific notation, but not quite, because in scientific notation, this number up front is supposed to be between 1 and 10. So it would have to look like, say, 3.0 times 10 to some power. Well, if I do that, if it was 30 and I make it 3.0, I'm just moving the decimal from here to there, so just one spot. So that would be times 10 to the first. That would be scientific notation for just this part. And you can check it, 3 times 10 is back to 30, right? But we still have this piece over here as well, times 10 to the negative 9. So to make it scientific notation, what we want to do is join those two parts together. So we have the 3.0 out front, that's between 1 and 10, so that's one part of scientific notation. And then times 10 raised to the, let's see, we're multiplying the bases, so we'd add the exponent, so 1 plus -9 would be -8. And then what were the units? Sorry, I stopped writing the units there, but we had nanoseconds to begin with, and then when we were done, everything was seconds. So this is seconds, 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 and then still seconds. So 3.0 times 10 to the -8 seconds would be how long it takes for a beam of light to go across a football field. And you know, that kind of isn't going to mean a lot to a lot of people, but if you think about what the 10 to the -8 means, it means move that decimal 8 spots to the left, so 0.000000003 seconds, right? So it's super fast. It's a very small amount of time. And just a quick check on all the scientific notation work we did by hand. If we just thought of this as a conversion from way back when at the beginning of the course, we would set it up, and then we'd start off with the 30, and then we'd say times 1 over a billion, and just press enter, and it tells us 3e to the -8, which is the same as 3.0 times 10 raised to the -8. There's the 3, there's the -8 for that exponent on 10. All right, let's try another one. There are approximately 2.2 million marriages per year in the U.S. Express this quantity in marriages per hour. So this is a problem that they refer to as putting numbers in perspective. So they're thinking 2.2 million is a big number. It's hard for people to process. So to tell them there's that many marriages per year is just kind of overwhelming. They can't even think about what it really means. So expressing it in marriages per hour allows us to make this number smaller and make it a little bit more digestible. But ultimately, it's just a conversion problem. So 2.2 million, and they said it was marriages per year. So per year means over years. And they want us to change that to marriages per hour. So the first thing I'm going to do is get rid of the million. So I'm just going to write that that's 2,200,000. Right, 2.2 million. So there's the millions place, everything else is after it. There's that 2 in the millions place, and then after it. You could also just go 2.2 times a million on your calculator. It does the same thing. Just show you that real quick. 2.2 times 1, 3 zeros, 6 zeros, and we have the same number. 3 zeros, and then the 200, then the 2. Okay, so now that's not million marriages, it's just marriages. 2,200,000 marriages is the same as 2.2 million marriages, so we took care of part of the conversion. But we still have years, and they want hours. So we start converting. Let's get rid of the years, and let's switch it to days. So there's 365 days in a typical year, and now the years are canceled, and we're in days. And let me just do another conversion factor over here on the next line. I guess let's just throw another conversion factor on there. I kind of ran out of space over here. But we don't want to have days. We want to have hours. So I'm going to put days up top so that the days up top here cancel with the days on the bottom there. And I'll put hours on the bottom to take over. And 1 day is the same as 24 hours. And then the days cancel. And we can multiply across to see what we get. So, kind of messy the way I've got this on 2 lines, but let's make it happen. So 2, 2, 0, 0, 0, 0, 0 is a match with that. And then times 1 over 365, and then times 1 over 24 from this other one right here. Multiplying those across, the starting number times the conversion to get to days times the conversion to get to hours, and we get this. So that is approximately 251.14, and what would the units be? So it was marriages, and after we did the conversions, it went from years to days to now to hours, so per hour. So this is kind of the idea. If it's overwhelming for people to hear there's 2.2 million marriages every year, then we could say that's the same as if there were 251.14 marriages every hour. And you hear that sometimes on the radio or in the news where they're trying to just make a number digestible for you. Like instead of saying that the U.S. is $20 trillion in debt, they might say that's as if every adult in the U.S. owes like $145,000 on the debt. So to kind of put it into a manageable size number instead of being so big that you can't process it, get it down to think about something simpler. So 2.2 million, maybe overwhelming, 251, not so bad. All right, so just a summary. We saw this a little bit before, but if you're trying to write a number in scientific notation, count the number of decimal places k that the decimal place moved so that the new number n meets the conditions that the number out front is between 1 and 10, and then however many places the decimal is moved, that's going to be your k. If it was I hate the left-right stuff that they use in the book, but if the decimal's moved to the left, then it's going to be a positive exponent. If the decimal is moved to the right, then it's going to be a negative exponent. The way I would prefer to think of this is when you have a big number to start off with, then you will move your decimal to your left and you'll get a positive exponent. And when do you get the negative exponents? When you had a really small number. So it's small numbers like 0.00037 end up with the negative exponents. It's big numbers like 8,657,412 end up with the positive exponent. So that's, I think, easier to keep track of. It makes more sense in my head to think big numbers positive, small numbers negative than this whole left-right thing. But they're both correct. I just prefer to think of it this way. The book writes it that way. All right, so we've been looking at exponents for a while. We looked at positive exponents back in Chapter 9. We started looking at negative exponents in this section. So why are we doing all that? And the answer is so that we can look at something called an exponential function. So let's go ahead and define that, and then we'll see why we need exponential functions. So an exponential function is a function whose equation can be put in the form f of x equals a times b raised to the x power. That number out front, a, is referred to as the coefficient, and that cannot be 0, otherwise that would just wipe the whole thing out. And the base has to be positive and not equal to 1, because weird stuff happens if the base is negative, or if the base is equal to 1, or if the base is equal to 0. And that constant that we're putting the power on is referred to as the base. All right, so that's what an exponential function looks like in its kind of abstract form. Let's look at an example so we can see a specific example of that, and also to see why do we care about these exponential functions. So the sales of LCD TV sets are shown in the table for various years. Let's let S be the sales in millions of dollars of LCD TVs in the year that is T years since 2000. The situation can be described by the linear function S equals 1487 times T minus 2823. It could also be described with the exponential function S equals 31.5 times 2.58 raised to the T. So use the graphing calculator to draw the graphs of the two models and a scattergram. All right, so first we'll set up the scattergram, and that means we need to convert these years to values of T. And it says T is the number of years since 2000. So 2001 minus 2000 is 1 year later. And then 2, 3, 4, 5, and 6. 2006 minus 2000 is 6. So what we're going to do now is put that data into the calculator. So we'll put the T's into L1 as our input, and then we'll put the sales of the LCD TVs into L2 as our output. So bring it in the calculator, hitting the stat button, going to edit, and enter those into L1. Whoops. Sorry. Stat, edit, and then I want to enter the number 1, 2, 3, 4, 5, and 6. Not sure what was going wrong there a second ago. Then go to L2 and type in these numbers, so 62, 246, and so on. All right, so we have all the data entered in, and now we want to do a scatter plot for that. So we want to do a couple things. We want to go to y equals and make sure the plot is turned on. It's not, so I'll do that. Turn on plot 1. It should be set up to be a scatter plot for L1 and L2. I can double check that real quick. Second stat plot. Plot 1 is a scatter, and it's for data in L1 and L2. Going to use squares to show the data. Now we want to make sure the window is right. So I'm going to hit window, and my t-values go from 1 to 6. So how about from 0 to 7 for my x-min and x-max, a little smaller than the min, a little bigger than the max, and a scale of 1 seems appropriate. If I'm going to go from 62 all the way to 8,480, I definitely don't want a number in ones. Maybe a scale like thousands or 500s would be good. So I like to think about the scale first if it's something other than 1, because when I go a little smaller than 1, I don't really want to do 61 or 8481, not when the scale might be 1,000. So what's a multiple of 1,000 smaller than 62? How about 0 for the y-min? What's a multiple of 1,000 bigger than 8480? How about 9,000 for the y-max? And now the smallest number fits, so does the biggest number, and it seems like we have a reasonable scale. All right, if I hit graph, I should see the data set. And here's the key thing to notice about that data set is that it's curving. And actually, I don't see that point very well, and I don't know if I'm seeing that point very well. So let me adjust the window. The 0 should be fine. Let's try going down to negative 1,000 so we can see below a little bit. So now we see this point a little bit better than maybe we did a moment ago. So 1, 2, 3, 4, 5, 6. We have all the points there. So what I want you to notice about this scatter plot is that it curves. It's got a curving pattern to it. So a straight line isn't the best fit. We could do regression. We could get the best fitting line, but it just doesn't seem like a line would be the best choice because of the curve. So the benefit of having these new exponential functions around is that they curve. So let's go ahead and enter these two functions into the y equals menu. So 1487 times x minus 2823. They're using t, but our input on the calculator is always x. And then for this one, 31.5, you don't really need the parentheses, times 2.58 raised to the t or the x. You could put the parentheses if you want, but you don't really need them as long as you hit the times right there. So when I graph them, the two graphs are going to get drawn in order. First the line, then the exponential. So let's hit graph and watch what happens. So there comes the line. It turns out that's the best fitting line you can do for that data set, but it's not a very good fit. Whereas the exponential, because its ability to curve, does a much better job of getting close to the point. So the reason they wanted us to draw both of those on there is to see how much better the exponential model does at fitting the points. Now they want us to start making some predictions. So they ask us to use the exponential model to estimate the sales of the LCD TVs in 2011 and then to do the same thing for the LCD TVs in 2011 using a linear model. So use the exponential model, also use the linear model. And the idea there is they want us to think about which of those is going to be more accurate. All right, so making these predictions is actually fairly straightforward. The first thing you need to do is figure out the value of t. T is 2011 minus the starting year of 2000, so t is 11. And if they want us to use the exponential model, use the function where the variable is the exponent, and say s equals 31.5 times 2.58 raised to the t, but t equals 11. And then we can put that into our calculator and see what we get. When they want us to do that for the linear model, we just use the other function. So s equals 1487 times t, but t is 11, and then minus 2823. So we're going to go ahead and make those predictions, just plug them into the calculator and get them. But in terms of this last question, let's actually answer that first, and then we'll go back and we'll fill those in. Which estimate would you expect to be more accurate? Well, let's look at the graph. Which of the two graphs fit the data better? Was it the line or was it the exponential function? It was by far the exponential function. So if you were asked to use one of those two equations to make predictions, it seems like the one that would be more likely to work would be the one that fits the data better. So I'm going to answer this question before I even see their answers. So which would you expect? Even the word expect almost seems like before we know the answer, right? So which estimate would you expect to be more accurate? I would expect the prediction from the exponential function to be better or more accurate. And then in terms of, for the explanation, I would say because the exponential function fits the curving data pattern better. So when one function fits your data better, you'd expect it to have more accurate predictions. Now, as far as how accurate either of these would be, we shouldn't have too much faith in it because our data goes from 1 to 6, and they're asking us to make a prediction for t equals 11. So that's an extrapolation, and anytime you extrapolate, you can't be that confident that you're going to get accurate answers regardless of which model you use. But let's go ahead and make the two predictions because they did ask us. So 31.5 times 2.58 raised to the 11th power would be 106,2006.853. There's a temptation to just throw a dollar sign in front of that, but if you look, the units are not dollars, they're millions of dollars. So that's times $1,000,000. And if you do that, you can put the dollar sign out front and just go times 1,000,000. Yeah, it switches to scientific notation. I was a little afraid of that, but this times 1,000,000 is just going to move our decimal 6 spots to the right. So 1, 2, 3, and then zeros. So 106,2006,853,000, moving 6 decimals to the right because of the 6 zeros on the million. So comma, 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 comma. So we've got millions, billions, just over $1 trillion is our estimate. Now the truth is that's probably not very accurate like they asked us about down here, but that's because it's an extrapolation. This is still the better model to use because it fits the data better. Doing the linear one, 1487 times 11 minus 2823, we get 13,534. That is also in millions. So we can multiply by 1,000,000. And that comes out in scientific notation too. So instead, I'll just put the dollar sign and 13,534. And then because of the times 1,000,000, 6 zeros. And then get my comma in there. So the linear one is predicting 13 billion. The exponential is predicting 1 trillion. If I had to pick one to go with, I would go with this one because it fits the data better. But the truth is they're probably both wrong. This is probably too much money. That's probably not enough. And the reason we're not getting accurate predictions is because we're extrapolating. But this is still the better choice, is to go with the function that fits the data better. And we'll continue to explore that as we move on through this chapter and the next one actually. So hopefully we'll get better and better at that idea. But given a choice, if you are looking at a graph that has a scatter plot that is curving, it seems like it would be better to make predictions with a model that curves than with a model that's straight, and this new exponential function is going to give us the ability to do that, and like I said, we'll continue to explore that as we move through this chapter and the next.